let's rigorously prove that limits of sequences are unique. And while this might seem intuitively obvious, we're going to give a rigorous proof based on the epsilon-n definition of a limit, and we're going to introduce the subject of real analysis, the theory of sequences, and mathematical proofs. Watch till the end for an introduction to the world of metric spaces as connected to this statement, which states that the limit of a sequence of points in n-dimensional Euclidean space is unique. If it exists, which it might not, but if it exists, there's only one possible limit. Now another way of saying this is that if we have two theoretical limits, so if xk converges to x prime, which is a point in Rn, and if xk converges to x double prime, which is another point in Rn, then we can conclude that x prime is equal to x double prime. That's what we want to prove, and in order to prove that, we're going to dive into the world of convergence very precisely based on the epsilon-n definition made easy. So what this states is if we think about one limit of xk, so if we think about x prime, what we are looking for is that no matter how close I get to x prime, okay, and closeness is going to be measured by what we call an epsilon ball containing x prime. Okay, so this is going to be inside of Rn, and it's going to be an epsilon ball which we denote by b of x prime epsilon. Okay, so this means all points within a distance of epsilon from x prime, which is the center of the epsilon ball. So we can write that as a set of all y in Rn such that the distance from y to x prime is less than epsilon. And here this is a function, it's going to be suggestive, it's going to take us into the world of metric spaces eventually, but it's just the distance from y to x prime in Rn. If you like, sometimes people denote this by the norm of y minus x prime. Okay, so if you think about vector spaces, for example, it's the norm of y minus x prime. It can be found using the Pythagorean theorem by taking the square root of the sum of the squares of the differences between the coordinates, but you can just think of it as a distance. And what we want to ensure is that no matter how small we take epsilon, okay, which is now going to be the radius of this ball, we can always ensure that the terms of the sequence are eventually in that ball. Okay, so if epsilon greater than 0, then there exists a big K such that, so little k greater than or equal to big K, we can ensure that the distance from xk to x prime is going to be less than epsilon. So eventually all the terms in the sequence beyond the kth term, the big kth term, is going to be inside this ball. Okay, so we can sort of write it using a red pen. We can write it as just, it doesn't matter, but they're just all going to be inside this ball, no matter how small we choose the ball. Okay, and that's going to be the statement that's down there. So it's very important that eventually all of them are in that ball. Doesn't matter as long as, you know, the first million terms or billion terms need not be in that ball, but as long as eventually all the terms are in that ball and stay there forever. That's what we care about. So that's what it means for the limit to be x prime. Now let's think about what it means for the limit to be x double prime. For the limit to be x double prime, we need the same condition for x double prime, and this is going to be hard. Immediately you can see that they can't get close to x prime and x double prime. But let's make this really precise. So for example, for x double prime, we're also going to have the same condition, and it's possible if the balls overlap. Okay, so I'm just drawing an oval here. It's not really a ball, but if the ball overlaps, okay, so maybe I can write this as if this is going to be x double prime, then it is possible for all but finitely many terms of the sequence, that is beyond a certain point, all the terms to be in both balls. However, if you choose the ball to be sufficiently small around x double prime, instead you choose a ball like this, which is the inner ball, it's not possible for the terms of the sequence to eventually be both in this ball and the smaller ball over there. So we need to derive a contradiction using that approach. So let's be very precise here and choose our epsilon carefully so that both these balls are disjoint, containing both x prime and x double prime with a radius of epsilon. And I'm going to erase this picture and draw the balls again so you can see it very precisely. So let's now draw the balls. So imagine we have two limits, x prime and x double prime. What I'm going to do is I'm going to choose an epsilon so that the ball containing x prime of radius epsilon and the ball containing x double prime of radius epsilon are disjoint balls. So what epsilon should we pick? So the maximum epsilon we can pick, if we think about the distance from x prime to x double prime inside Rn, so whatever this distance is, it's going to be d of x prime x double prime, and we're assuming for a contradiction that it's non-zero, okay, that it's greater than 0 because we're assuming these are two different limits and we want to show they're the same. Then what we can do is we can take a ball that is a radius of half of this distance, okay? So I can do one here and I can do one here, And now you are going to try to show that these two balls are disjoint, and we're going to be very rigorous about this and tie it into an important axiom for metric spaces. Okay, so watch forward for that. So what epsilon we're going to pick is we're going to pick epsilon is equal to the distance between x prime and x double prime divided by 2. And now I want to show that using the definition of convergence, we cannot have x converging to x prime and x double prime if we take this value of epsilon. So let's now go into the proof. Okay, so our proof is going to be assume for a contradiction that x prime and x double prime are limits of the sequence xk. Okay, so in particular we know that there exists, okay, so we can say there exists k prime such that for k greater than or equal to k prime, we know that the distance from xk to x prime is going to be less than epsilon. Okay, that's number one. Number two is that there exists, and this symbol means there exists, k double prime such that for k greater than or equal to k double prime, and this is little k is the index of the terms in the sequence, we know that the distance from xk to x double prime is going to be less than epsilon. Now, here's the point. If we think about our x, its distance, so imagine our hypothetical x, which I'm going to draw with a red marker, its distance to x prime is going to be less than epsilon. Its distance to x double prime is going to be less than epsilon. But then that's going to imply the distance between x prime and x double prime is also going to be small in some sense. And that is the triangle inequality. Okay, so the triangle inequality tells us the shortest path from x prime to x double prime is going to be the direct path. So this detoured path is going to be longer, which we can express as an inequality. The inequality is going to be that the distance from x to x prime to x double prime is going to be less than or equal to the distance from x prime to xk plus the distance from xk to x double prime. That's going to be the inequality, and we know that as long as little k is bigger than both big K prime and big K double prime. Okay, so we know that for little k bigger than the max, okay, this is how I write it, the max of big K prime and big K double prime, we know that this is going to be less than, the distance from x prime to xk is going to be less than epsilon. The distance from xk to x double prime is going to be less than epsilon. So this is going to be less than 2 epsilon, which is just equal to the distance from x prime to x double prime. And that is of course a contradiction. We've said some number is less than itself. And the idea here is to encapsulate the fact that something cannot simultaneously be close to two different things by the triangle inequality unless both those things were originally close. And in the Epsilon-N definition of convergence, epsilon can be arbitrary. So we have picked off specific epsilon and we said in this particular situation, you can't be simultaneously close to x prime and x double prime. And now I'm going to show you a beautiful, so that concludes the proof that limits are unique, because that shows that the distance from x prime to x double prime could not have been positive. Okay, that's a very important way of phrasing the proof. And now I'm going to show you something beautiful with metric spaces. Actually, this d of x prime x double prime is generally applicable to metric spaces. This whole proof is generally applicable to metric spaces. Rn is an example of a metric space. You have a distance function. What is a metric space in general? I'm going to show that to you and show you how this proof applies to show limits are always unique in a metric space. A metric space is a function on a set. Okay, so we have a function d from x cross x to r, at least 0. Okay, so non-negative real numbers. Okay, and so it's a function, it basically pairs off two elements of the set x and y and spits out a number that is non-zero. Okay, that's what the first condition of a metric space is. And then you have the three conditions that it must satisfy. So condition 1 is that d of xy is equal to 0 if and only if x is equal to y. Okay, so that means that the distance between 2 points is always going to be positive if the 2 points are distinct. We have used that axiom in this proof, okay, because basically our proof says that we have assumed that the distance is going to be positive and then got a contradiction, therefore concluding the distance between the two limits was equal to 0, which implies the limits have to be equal. That is by this first axiom. Okay, so that's all we needed about the metric. We did not need to know how it was defined, that it was a norm or the Pythagorean theorem. We just need to know it satisfies this property. Okay, so you're axiomatically reducing everything down. The second condition is that the distance function of the metric, this is what is called the metric d, is symmetric. d of xy is always equal to d of yx for all pairs x comma y inside our space. Okay, and this is again something that we've used implicitly. Okay, we've used implicitly because when we sort of think about convergence, we don't want to think about distance from x prime to xk or xk k to x prime. We just don't care about the order. That is a symmetry axiom for metric spaces. And the last axiom is the most important, is the triangle inequality, that the distance between x and z is always going to be less than or equal to the distance from x to y plus the distance from y to z. That was crucial in our proof, just as the first axiom was, to basically show that you simultaneously could not be in two epsilon balls at the same time. Those two epsilon balls were disjoint if you took epsilon to be half the distance between the 2 points. And that relies on the triangle inequality. But that's all you need. So this proof that limits are unique applies in any metric space, which includes RD, but also a whole range of other spaces. And if you want to see more about metric spaces and real analysis, I'm doing it all on my channel, all levels of math. So please don't forget to like and subscribe. It means a lot. Lots of people ask for this. So before you click away, please just consider doing that, because it really helps disseminate my videos. It's all free. It's all accessible on YouTube. And all you have to do is click a button, which takes a second, and it makes a huge difference, especially if you've watched this far. Super grateful for your support. And if you're really loving my content, also please consider checking out my Patreon page. Links in the description. For small contributions there, they make a huge difference to my channel. I'm doing everything on my own to create exclusive, infinite, free, accessible math education. Everything's optional. I'm delivering it to you, and you can decide if you want to check out that page. There are exclusive perks. I'm really grateful for all the support, and I'm super excited to see you in the next video. If you want to see more real analysis, check out my playlist. It's going to pop up on the screen here. And another fun video on my channel you're going to love after this one is going to pop up here. I'm going to see you in either one, and I hope you have an amazing rest of your day.